I'm going to do a pretty intricate or a challenging homework problem in two different ways. This is page 191, number 50, and you want to look at the book, make sure you can understand the statement of the problem. First, find equations of both lines through the point 2, minus 3 that are tangent to the parabola y equals x squared plus x. So here I have that parabola graphed out. I made sure to do a fairly careful graph so it will look pretty correct. And here's the point 2, minus 3. Notice the scale is very different in x and y here, so I can fit the parabola on easily. So we're trying to figure out, are there some lines that go through this point that are tangent to the parabola? And indeed, it looks like if I shoot out here, maybe not quite here, but maybe a little further on, maybe that's going to be tangent to the parabola. And then over here, kind of looks like right about at minus 1, maybe. I didn't shoot it very well. That's okay. And what's hard about this is it's what I call a backwards problem. It's a problem where there's a sort of an unexpected variable to solve for. And what I like to encourage people to do, as just a general strategy of understanding, is try to figure out, try to look at these problems and figure out what the forward version of the problem would be. Let me zoom out here. And so let me actually talk about two different forward versions of the problem. So one would be let a equal, I'm going to pick a number that actually won't work on purpose. It looks like 3 is not going to work. Let a equals 3. Find the equation of the tangent line to y equals x squared plus x at a equals 3. And then a yes or no question. Let's say, does it pass through this point 2, minus 3? That's a forward version of the problem. It actually gives you a particular thing to calculate and asks a yes or no question about it. And this, what our real problem is going to be the backwards version, where they don't tell you this A. They say, I'm looking at a mystery point of tangency, and we want to find that mystery point so that the answer will be yes. And that's more sophisticated, but I want to show you how much of the techniques are shown by looking at the forward version of the problem. So that's taking 3 here and taking this tangent line. It looks pretty clear to me, I guess, that it's not going to go through that point. So we would expect the answer no. So let's do that version first. And let's see if you can see. Yeah, okay. So let's find the equation of the tangent line. Y equals x squared plus x. Y prime equals 2x plus 1. Now, I've said, I'm going to say this over and over again, that a big thing people don't do when they're taking the equation of the tangent line is you need to plug in the point you're interested in. Y and x are supposed to be variables. And throughout this whole problem, we're going to let those be variables almost the whole time and not think of them as numbers. We need something, we need to actually plug in the number. This y prime gives you the tangent line. It gives you the slope of all these possible tangent lines at any point x. And we're interested right now in just this one where x equals 3. And I've called that A to suggest some fixed point. I mean, when you use a letter from the beginning of the alphabet, it suggests a constant, a fixed number. So y prime equals 2x plus 1. And so y prime at A, at 3, is 7. That's the slope of our tangent line. Now, how do we find the actual equation of the tangent line? We need to figure out the point of tangency, and then we can use point slope. Okay, so that's the slope. And then the point is going to be 3, well, you need to plug that into here. Always go back to your master equation, the formula for the function, if you're stuck. See if that's what you're stuck on. 9 plus 3 is 12. So our equation is going to be y minus 12 equals 7 times x minus 3. Okay, now, how do we ask Does that pass through 2 comma minus 3? How would we figure that out? We plug in 2 for x and minus 3 for y. When we've got an equation of a line, and somebody's asking you whether a certain point is on that line, well, that's what equations are for. They're for testing whether a point is in a certain set. And we're going to test, is this point on this line? We expect the answer no. So is 2 minus 3 on this line? And we're going to plug in minus 3 minus 12. That's minus 15. That's the left-hand side. To the right-hand side, we're going to take 7 times 2 minus 3. That's minus 7. These are not equal. So the answer is no. So that's the forward version. That has a lot of good calculus stuff. Taking a derivative, using it to find the slope of a tangent line, plugging in a point slope, getting an equation of a line, and then using that for something. Now we're going one step further. Okay, so that was the forwards version. What's the backwards version? It's really similar. But instead of being given this number and then asked the yes or no question, it just flips it. It says, let's try and find a mystery point. Let's call it A, because we don't really want to think of it as a variable, even though we're going to solve for it. We want to think of it as a fixed number. It's just some number, but we don't know it yet, so it has to be a letter. So A is a pretty good letter for this. It's a very standard letter for this use. So we're going to redo the calculation. Everywhere we see a 3, an A is going to come in. But we can still do the calculation. That's the great thing about knowing how to do algebra. You can do things with letters instead of numbers. So the backwards version. So this is one way to do the real problem, number 50, is you take y equals x squared plus x. Y prime is still 2x plus 1. And so y prime, the slope at this mystery point A, is going to be 2a plus 1. And you might wonder, why is it such a big deal to change the letter from x to a? I'll show you in just a second, because x is going to have its own role. So that was the slope. Now we plug in the point. Ooh, the point also has a's in it. The point, so that's the slope. The point is a, comma, and then you just plug in. Remember, our equation is y equals x squared plus x. If you're plugging in x equals a, then the value here is going to be a squared plus a. And the letters are really proliferating. A is showing up everywhere. But that's okay, because what we're going to get eventually is an equation for a. One of the main things about being able to do these problems is just going with the flow and realizing that it's okay for a's to show up in everything. Now I can calculate the equation of the tangent line. And this is actually going to be a very cool thing. Y minus the quantity a squared plus a, crucial parentheses there, equals the quantity 2a plus 1 times x minus a. And let's think about what a powerful thing we have here. This is a master formula for the equation of the tangent line to any point on this parabola. You tell me a point A, 1, 2, 3, pi, e minus 7, or whatever, I can very quickly just whip out from this formula what the equation of the tangent line there is. Why is that so useful here? It's because we have an unknown tangent line, in fact 2 of them, that are supposed to satisfy some property, and we want to figure out what those are. So what we do is, let's look at what we did in the forwards version. That last step in the forwards version was we took the equation of the tangent line, and to figure out if a certain point was on the line, we plugged those in for x and y. Okay. So here's where it's really, really crucial that x and a are totally different letters. A is the point of tangency. We want to think of that as a constant. X is something that runs along this tangent line, and y is something that runs along that tangent line. We need to let that be free to vary independently. It's a little bit of a sophisticated thing, but it works out. So I'm going to plug in minus 3 minus a squared plus a equals quantity 2a plus 1 times 2 minus a. I'm plugging in 2 for x and minus 3 for a. And I'll continue this in the next installment.